Let's take a look at section 1.4, just some of the highlights from the homework that I want to emphasize, a couple things that maybe weren't in the video. So we'll start with this one, which in WebAssign is going to look like this. Number B here, is the expression square root of x plus 4 equal to x plus 2? That's a great one. I like this one. This is just kind of maybe a selfish reason here that we're covering this. But it really looks and feels like you should be able to distribute that square root sign, the square root of x squared plus square root of 4. But does it actually work? Can you do that? Well, let's do what Einstein would call a Gedankendenken experiment, a thought experiment. And that is, what if we choose a value for x? Just pick a simple value for x, like 3. All right? Let's see if it works there. So I'll try it over here. If I put in a 3 for x, that'd be 3 squared plus 4. Does that equal 3 plus 2? Well, that'd be the square root of 9 plus 4, or the square root of 13, and I don't think that's equal to 5. So the bottom line is, as tempting as it looks, you can't sort of distribute the square root symbol. It just doesn't work. So, all right. Couple other ones. Something that's not really in my video there that you're going to need on the homework is work with complex fractions. I mean, some of this is kind of implied, I guess, and in a way you've experienced complex fractions. For instance, this one right here. So let me copy that one down. I always kind of was amused by the name complex fractions. It feels like fractions are already complex, but yet somehow we have a complex fractions. How is something that's already complex more complex? Well, it's more complex when you have a fraction within a fraction. So x cubed over x plus 6 divided by x over x squared plus 12x plus 36. So the video did practice stuff like this. You just didn't see it in this form. Now the way that we can work this is by realizing that the numerator is itself a fraction, and so is the denominator. So I got a fraction here and a fraction here. What's the rule for dividing by a fraction? What do you always have to do when you divide by a fraction? There's a multiply by the reciprocal. Perfect, thank you. So that's going to be x cubed over x plus 6 times the reciprocal here, which is going to be x squared plus 12x plus 36 over x. Okay, good. Now, you can't just go canceling, say, the 6 into the 12 or the 6 into the 36. You've got to factor these things first. So let's see about that. The numerator here, we're good. The denominator here, we're good. But the numerator of the second fraction, we can factor that. So I'm going to write this as x plus 6. I'm going to put parentheses around that because we have to treat that as one whole object. How about the numerator of the second fraction? Can anyone tell me how that one factors? What times what?
6 and 6.
All right, we're going to need a 6 and a 6. And everything has to be plus here. Thank you, Carl Espy. And then in the denominator, we still have that x. Now, in different circumstances, I'd probably prefer that you write this as x plus 6 quantity squared. But we don't need to for this problem. For this problem, it's good enough just to realize that we've got an x plus 6 twice in the numerator. And so this is the fun part. You take out your Zorro pen, give it a nice ole. Cancel that, and we're looking good there. But we're not quite done with the cancellation. What else can we do? One of the x's leaves me with an x squared. So overall, in the numerator, I'll be left with an x squared times x plus 6 over 1, technically, but I don't need to write that. You don't have to distribute this unless, the problem says to. If you wanted to distribute it, that's fine, but either one is good. So how are we looking there with the complex fraction one? Doing good? All right. Thank you. Thank you. If there's some questions, please chime up. Let me know. If you're at home on Zoom or if you're in class, let me know. Let's try some more here. Another complex fraction. This one's going to work different, and it's because it's going to look different. So next one is to simplify this complex fraction, which is x minus x over y divided by y minus y over x. Now you can't just do that kind of invert and multiply thing like we did with the last one, because the numerator is not just a nice whole fraction. I've got a couple terms in the numerator. So for this one, I would suggest something a little bit different than the last one. So I'm going to move over here and give myself a little bit more room. When you're working with an expression, not an equation, remember, this started out like this. There's no equation here. The only thing you can do with an expression is simplify it. So our only trick in simplifying something like this is to multiply by 1. Now the form of 1 that I'm going to choose is going to be kind of clever. I want to choose a form of 1 that's going to help me get rid of these denominators. These are called secondary fractions. So the primary fraction is this big one. It's got a numerator and denominator. And in the numerator and denominator, we have these secondary fractions. I want to multiply both sides, both numerator and denominator, by the LCD of the secondary fractions. So let's take a look at our secondary fractions. Got that and that. Those are my denominators. What would be the lowest common denominator for these two fractions? X, Y, right? You got one of each. So what I'm going to do is I'm going to multiply by 1 in the following form. I'm going to multiply the numerator by xy, and I'm going to multiply the denominator by xy. Xy over xy is 1. Something over itself is 1. But instead of canceling here, what I'm going to do is I'm going to distribute. I'm going to distribute this term to the first term and the second term. And likewise in the denominator, that xy is going to have to distribute itself to both terms. Okay. So let's write that out. Let's see what that's going to equal. In the numerator, I'm going to get xy times x. That's going to give me 2 of the x's there. So x times x would be x squared times y. When I distribute here, well, I'm still going to get an x squared because I'll have an x times x. But what about the y's? What's going to happen with the y's? Yeah, one of the y's is going to cancel out. So that'll cancel with this, and it's just going to leave me with an x squared. Take a second and see if you can't figure out what's going to happen in the denominator. Try and distribute in the denominator and see what's left. So let's take a look here. In the denominator, I have an x times y squared. And then when I distribute this here, I'll just keep the negative sign, distribute that here. The x's cancel. So what's this term right here? Y squared. Excellent. No pun. If I wanted to, I can notice that I can cancel, or I can factor out an x squared from the numerator, which leaves behind y minus 1, and a y squared from the denominator, which leaves behind x minus 1. But that doesn't give me any extra cancellation. It's not like I can cancel these terms. They're different. So as far as I'm concerned, you can leave the answer this way or this way. You should get used to the fact that sometimes you are going to get some extra cancellations, so you should look for that. Try and factor this out when you're done. etc. Okay. Let me give you a couple review items before we do the next one. The next one's going to be a little bit challenging. So I want you to recall a couple things. Rats. Little Photoshop here. What happens when you multiply things with the same base? What happens to add the exponents? Thank you. And if you divide things with the same base, subtract them. Excellent. And let's do one more thing. It's kind of a reminder, but it's something you probably don't think about like ever. And I don't blame you. It's okay. Suppose we had 6x plus, I don't know, 18. Now, a lot of you in your head could probably factor out that 6 for me. If I factored out the 6, what's left in the parentheses? Yeah, x plus 3. Perfect. So we do it without even thinking. It's just bam, x plus 3. But let's understand the hidden step, what's going on in between here. And that is, when you factor something out like a 6, what you're really doing is you're really dividing both of those terms by the term that you factor out. So dividing this by a 6 and this by a 6. So what happens? The 6's cancel, leaves me with an x. 6 goes into 18 3 times. All right. So big deal, right? Well, why do I care? Well, it's helpful to know and understand this when you're doing problems like the next couple. So let me show you those, and then I'll copy them down while you copy them down. So they're down here, for example, F. This is stuff that you're going to run into in calculus when you do the quotient rule. So I want you to be good at this now so that when you take me for calculus, you're like, oh, I got this. I remember this. So let's copy that down. And I'm just going to grab myself a fresh chunk of paper here. 6 times 8 plus x to the 1/2 minus x times 8 plus x to the negative 1/2 divided by 8 plus x. So I'm going to switch screens here. Here's a problem I just copied down. Now there's a trick in simplifying this, and it actually will simplify pretty nicely, much more than you might think. The trick is, when you've got things like this with these fractional exponents, you want to factor out the largest negative exponent. So that would be this one. So let's see what happens when I do that. So I'm going to factor out 8 plus x to the negative 1/2 from both terms in the numerator. Now this may get a little cumbersome because we have to do a fair amount of writing, but it does make it easier to see what's going on. So when I factor something out, and I just mentioned this, what do I have to divide each of these terms by? What's going to go in the denominator of this? Eight plus x to the negative 1/2. And 8 plus x to the negative 1/2. That term is what I factored out, so that term has to divide each of those terms in the parenthesis there, or in the brackets. All right. Now there's some nice cancellation and simplification that happens here. Does anyone see anything on the easy side? What's the easy thing to cancel or do here? Yeah, this and this are identical. So they cancel out completely. So that's nice. And now the other thing is this one right here. And I kind of gave you a heads up on that right here. When you divide things with the same base, you subtract their exponents. Well, guess what? These things have the same base. So I should subtract their exponents. So the question is, right here, what do I get when I take 1/2 minus negative 1/2? What does that give me? Well, that becomes a plus, right? So 1/2 plus 1/2 gives you 1. Nice. So what am I left with then? I'm left with 8 plus x to the negative 1/2 times 6 times 8 plus x to the first power minus x. So I subtracted the exponents here. I got a 1. These canceled out. It just left me with an x. Do I really need the 1 there? Do I need to write 1? No. It's just kind of understood. So you don't have to write it there if you don't want. I'm going to do two things here. I'm going to distribute this 6 to both of these terms. And then I'm also going to take this down to the denominator. Because if you've got a negative exponent, you can get rid of the negative in the exponent by moving that term to the other side of the fraction. So it's going to look like this. 48 plus 6x minus x. And in the denominator, that's going to be 8 plus x to the positive 1/2 times 8 plus x. We're almost done here. 6x minus x gives me 5x plus 48. And in the denominator, I can simplify that as well. What's the rule when you multiply things with the same base? What do you do with their exponents? Add them. And even though it's not written, it's understood that there's a 1 here. So 1 plus 1/2, 1 1/2. Probably just convenient to write that as 3/2. So there you go. That's the exact same expression that we dealt with just a minute ago. It's just in a different form. So, all right. Comments or thoughts on that one? All right. That's towards the end of your homework, but there are a couple there. If you need some help on them, get it. But other than that, let's get busy on the homework.